So we start a chapter on Exergy. And that word Exergy should look very familiar to another word that you're very familiar with. What is that other word that you're very familiar with? Energy. And so what's the difference between it? Just one letter. And what do you think? Do you think the person who coined and introduced the term Exergy knew what they were doing and just changed one letter because they're very similar concepts and very similar? Yes, of course. Yeah. So this is just like energy, but it's a particular property called Exergy. All right, so we're going to do this. We're going to introduce the new property, Exergy, what it means, how it's useful. We'll be able to calculate it and then apply it for a system that is a closed system undergoing a process. And then we'll have a modified Exergy, a flow Exergy, and that will be applicable for open system analysis, control volumes, maybe analysis of a turbine, a compressor, a pump, a nozzle, diffuser, expansion valve. And then we'll talk about a second law, or exergetic efficiency. Just like we had isentropic efficiency, now you have another efficiency, which is very similar in magnitude, but is different in definition. It's not the isentropic efficiency. It's the exergetic, or the second law efficiency. And we can do it for a turbine, a pump, a compressor, and you can also do it for a heat exchanger, although I don't try and stress it because heat exchanger analysis, exergetic analysis of heat exchangers can be a little tricky. Okay, let's get into it. If you're encountered with a new word, used to be go look at a dictionary. Well, the online dictionary or encyclopedia is available. Most people can quickly do that. So if I just say define this word because I want to learn about it, Exergy, I'll come back with something like this. Is the energy that is available to be used. Okay. After the system and surroundings reach equilibrium, the Exergy is 0. All right. Determining Exergy was also the first goal of thermodynamics. That last sentence is really interesting. It really was. What do you think the origins of thermodynamics were? Steam power, steam engines. Burn something to turn something. Burn to lift, do work. This was very novel. If you wanted to lift something before, you used muscle power, human or animal muscle power. But you could light a fire, and it would not only get something hot, but it would actually lift something, do work, pump the water out of a deep well or mine. Yeah, that's it. And that was a revolution that really started the Industrial Revolution. Okay, but this idea is we struggle with this term Exergy. Now, how many people have passed Thermo 1? Everybody. How many people know that Thermo 1 was all about energy, the conservation of energy, the transformation of energy between forms, and the limitations on the transformation of energy between forms? What word did I say most in all that summary of thermodynamics? Energy. You know energy. Everybody knows energy. But if you've taken me for Thermo 1, you also know that I challenge you to find the definition of energy in the thermodynamics textbook. Did you look? Do you think there's a nice, clean definition of energy in our thermodynamics textbook? And I'm about ready to give a nice, clean definition of Exergy, which is in our thermodynamics textbook. But there's no clean definition of energy in it. But most of you would say, okay, energy, I know what that is. I spent a whole class, thermodynamics, studying it, using it, manipulating, calculations, galore. I'm an expert. All right, what is the energy? It's the ability to do work. That's the typical answer given. If you Googled it, you'd probably find it like that. Guess what? That's a great definition of Exergy, the ability to do work, to do something useful. It's not all of the energy can be converted into work. Only some of it. And that's really one of the key ideas in thermodynamics, the limitation between the transformation of energy and forms, and especially the most useful is work, what we desire, shaft work, lift something, mechanical energy. All right. So this is our textbook definition. Exergy is the maximum theoretical work. You're probably not going to get there, but it's the theoretical maximum work obtainable from a system working with its environment. It's in concert with the environment. It's like together. These have to be considered together. As the system starts from some initial state and undergoes, there's that word again, theoretical process. And the final state is when the system is in equilibrium with what? Its environment. That's why the environment's part of the definition of the exergy. That's a lot to swallow. I'd encourage you to reread it, and not just have me try and say it 10 times and then you try to grasp it. But we have a system, and I'm going to derive it in a second. And maybe it's hot and high pressure. And somebody says, I would like you to take that system and get the most energy out of it. Well, you say, you know what? I'm going to be able to transfer some heat and try to make some work out of that. But eventually, that temperature of the system is going to drop. What's the lowest that it can drop to? Well, when it comes into thermal equilibrium with the environment. It doesn't make sense to start out with something that's 300 degrees C, have the local environment 25 degrees C, and the system's going to go to make as much work, but it's going to end up at negative 100 degrees C. That don't make any sense. If I started at negative 100 and went to 25, I could actually get work out of the system. If I start at 300 and go to 25, I can get work out of the system. But when I'm at 25, I can't get any more work out of it. It's the same temperature. It's in thermal equilibrium with the environment. Let's say I start the pressure, 1 megapascal pressure. And the local ambient pressure is 1 atmosphere. Let's round it off to 1 bar, or 100 kilopascal, or 0.1 megapascal. Hey, I got a high pressure. I can expand. I can do some work. But once I get the pressure down to 0.1 megapascal, 1 bar, I can't make any more work out of the system. It's in mechanical equilibrium with the environment. Somebody says, well, why don't we start with a vacuum? 0.001 megapascal, that's a vacuum. Well, you'd be clever enough to start from a vacuum and get the system up to a pressure, of atmospheric pressure, 0.1 megapascal, and still make work. So it's a little tricky. I like to say that think it's hot and high pressure, but it also could be super cold and a vacuum, and you could still make useful work. But once it gets to what? Thermal equilibrium with who? And mechanical equilibrium with the environment, you're dead. You can't make any more work out of that system. Make sense? Good. Give me the final exam then. All right, so exergy, you'll see it described as this. It's that portion of the energy which can be converted to do useful work. Great. Or it's the measure of the quality of that energy. Good way of describing it. Or it's the maximum useful work. That's good too. All these phrases are the same idea. So what we find is exergy is a property. What are the properties are you familiar with coming out of Thermo 1? Well, pressure, temperature, specific volume, internal energy, enthalpy, entropy. So now we're going to add to the list exergy. You can have the total exergy or the specific exergy, but it's just a property. It's just a property of the system. But it's a very unique property of the system because not only does it depend on, let's say, temperature and pressure fix the state, or pressure and volume fix the state, or pressure and internal energy fix the state. What you can find is this is really the state of the system expressed by its other properties. But it also is a function of the properties of the environment. The two important properties of the environment, when you reach thermal equilibrium, the system is at the environment temperature T0. And when you reach mechanical equilibrium, the pressure of the system is the same as the pressure of the environment, which is P0. So this P and this T with those subscript naught on it are the environment temperature and pressure. Make sense? All right. And not only is it a function of the properties of the system at its current state, but it's a function of the properties of the system when it doesn't have to get there, but when it would theoretically get to be in thermal and mechanical equilibrium with the environment. And this is a point of confusion. So you say, oh, that's V naught, that's U naught, and that's S naught. What exactly is V naught, U naught, and S naught? And you have two choices. It's a property of the environment, or it's a property of the system. Which one is it? Which one is it? Is this V, the specific volume of the system, or is it the specific volume of the environment? Who's brave? You're brave. I need another person.
The system.
You're brave. You are very brave. Don't give up on me this semester. But maybe let Eager Beaver over here try. It's a tough concept. Because what did we just say about the P naught and the T naught? What are those? That subscript says it's the pressure of the environment. But this is a very long sentence right here to describe V naught, U naught, S naught, which says it's the theoretical, if the system would actually get to become in mechanical and thermal equilibrium with the environment, that would be the property of the system. Yeah.
Like 0.001.
Yeah. Yeah. Yep. So a lot of times this temperature is 25 degrees C, and this pressure is 1 atm or 1 bar, close enough. They're close to each other. Okay? Okay. So you can see this is a complicated property. It's not simple. Well, what is this system when it gets to become in thermal and mechanical equilibrium with the environment? We then claim that the system is dead. Think about it. You're laying on the couch, long day. Somebody says, get up and help do the dishes. I have no energy. I am dead beat, tired. I'm just laying on the couch. Well, same concept here in thermodynamics. The system, when it's in thermal mechanical equilibrium with the environment, it is not capable of producing any more useful work. And it is said to be at the dead state. So when you have thermal equilibrium, the temperature of the system is equal to T naught. And when you have mechanical equilibrium, the pressure of the system is P naught. One thing I forgot to point out on this previous slide is take a look at these three subscripts on V, U, and S. Do they have the same subscript, all three of them? And that's the same throughout our textbook. Sometimes it'll look like this, a letter, a lowercase letter. Sometimes it'll look like this, a number like 1, 2, 3, but the number would be 0. So what does this look like right here? The number 0 is a subscript. What about this one? Lowercase letter 0. Letter, not number, letter. Right? But all I say is you look carefully through our textbook and you'll see examples like, that looks like a number, 0. Oh, that looks like a letter O. Just get used to it, right? I like to think of it as state number 0 as the dead state. And then I like to go around and say state 1, state 2, state 3 in my cycle analysis. So I like to put it as state number 0. But then I often will just say naught with a lowercase letter O. Okay? All right. So what did I write here? What does that look like? The number or the letter? The number. Yeah. I'm just trying to help you. These are small nuances. All right. Now let's go ahead and compare what we are very familiar with, energy, right, with the new property, exergy, energy. And we are going to contrast it with exergy, a little table to help us see things. We were able to do an analysis of a closed system using energy. Do you remember that? And we would write the first law, energy balance. I'm not going to write the exergy balance. We haven't done it yet. But the energy balance will be something like, oh, the change in the internal energy of the system is equal to Q, how much heat came in during the process, 1 to 2, minus the work out, 1 to 2. Remember something like that? First law, energy balance. The key idea was cap U, which was, no, I'm sorry. Let me do this again. This is cap E in most general cases. So the change in the energy of the system in 3 forms: change in cap U, change in KE, change in PE. Oh man, I forgot. What does PE stand for? Potential energy. What does KE stand for? Kinetic energy. And what does cap U stand for? Internal energy, and cap E is total energy. So sometimes you'll see as E is equal to U plus KE plus PE. Sometimes you'll see it that way. Or they drop the lowercase e's and u's and lowercase KE and lowercase PE. Per unit mass, specific, that's right. It's per unit mass instead of the total. And then sometimes you'll write it U plus V squared over 2 plus GZ. What do you think? You just flushed out what the kinetic energy is, specific kinetic and specific potential energy are. True? So that we would do a first law analysis of a closed system using internal energy and the kinetic and potential energy. What about for an open system? Can you remember? Oh, let's write it down. The change in the energy of the control volume with respect to time is equal to the rate at which what flows in with Q? Heat. Minus W dot out of the control volume, some power. And then we had plus some mass flow rate coming in with, what did it bring in? Enthalpy plus, you can write it lowercase ke and lowercase pe, all on the n minus m dot with the h plus ke plus pe on the exit. So this inlet exit, if they're one inlet, one outlet, it's the same as mass flow rate, right? Steady state goes like this. But the key idea was this group of terms, H plus KE plus PE. Did they introduce something like this? Did they introduce E sub F and say, hey, this is the specific energy, this is the specific flow energy? Did they have a new symbol, E subscript F in the energy? No, they did not. You'll see that they always had just H plus 1/2 V squared plus GZ. All right, but they could have introduced flow energy. They just didn't. All right, what was this term defined as, this H right there? It's U plus PV, and the name of H is enthalpy. You're going to say the same pattern in exergy analysis. I'm not going to write the exergy balance. I'm just going to say the key property when you're doing a closed system analysis is just exergy. And if you're doing an open system analysis, it's a modified exergy. It's called the flow exergy. Okay, so what is the exergy? Well, get ready. Remember, it was a function of the property of the system, and it was a function of the dead state temperature and the dead state pressure, and the theoretical properties of the system like U's and V naughts and S naughts. That would be of the system if it actually, when it gets into thermal equilibrium with the environment. So there's a lot of symbols in this exergy. So let's start. They use a lowercase e for exergy. It's going to be the U minus U naught. Let's understand those two terms right away. It's two internal energies. Is one of the internal energy of the system, and the other the internal energy of the environment? Or is it of the system when it is in mechanical and mechanical thermal equilibrium with the environment? Yes. Tricky, isn't it? It's tricky right there. And we continue on. We have plus P naught. What's P naught? The pressure of the environment, the dead state pressure. Then we have V minus V naught. Hey, that's just like U minus U naught. It's the current specific volume of the system. Subtract from it the specific volume if it would become in equilibrium with the environment. Okay? Oh, it's not done yet. I didn't leave enough room, sorry. We have minus T naught. What is that T naught? Temperature. S minus S naught. What is the S's? Entropy of the system in its current state and the system at the dead state. Now, do you think I can just put T in degree C, or do you think I'm going to have to put in T in Kelvin absolute temperature scale? I better put it in absolute. And all of the pressures we work with in the tables and everything else, they're already absolute pressures. There's very few things that are gauge pressures in our tables and textbook. So this is absolute pressure, absolute temperature. All right, and I didn't leave enough room, but I have to wrap it around. What do we have? We're going to have the 1/2 V squared and the GZ. I could write it as KE and PE, but those two tag along just like they did. What is the difference between this symbol and that symbol? They look alike, Professor. They sure do. Maybe before earlier versions they tried to subscript or bold or do a little syntax or something to make it look different. Or maybe they had it as a Greek letter. Or a different book would have it as Greek letter to distinguish it. If you read the textbook carefully, they say, well, you know what? We're just going to use the same symbol because they're very similar concepts. But you have to know what you're doing as the user, as the analyst, and you have to look at the context to know exactly what it is. And that E could be exergy in chapter 7, and it could be energy in chapter 2. That's engineering. Yes?
Why do you use P naught and not P average?
P naught?
Yeah, like P sub 0.
That's the dead state. That's just a syntax for what is the dead state pressure.
But don't you normally use like P average for like calculating work?
No, let me move on. No, it's not. You're gonna. Okay. So how about just, Professor, you didn't derive that for us. I want to do it before we end today. Okay. So I'm a little bit of a rush here. So the next one is E sub F. What is that? Flow exergy. What is its definition? Thankfully, for open systems, it's a lot simpler, not more complex than for a closed system. An open system, flow exergy, you would have H minus H naught minus T naught, S minus S naught, plus the kinetic energy, plus the potential energy. I hope you realize these are exactly the same, right? Specific kinetic or specific potential energy, I could express it. Lowercase ke or 1/2 v squared. Doesn't it look a little simpler? So we do see the enthalpy pop up in the flow exergy. Okay? All right. Let's do this. Let's go back and say the key parameter for energy analysis closed system was U. U is internal energy. Just to review. What were the units on lowercase u? Specific internal energy. Professor, I need my equation sheet. No, you don't. Kilojoules per kilogram. All right. Then we had the next property, H. H was enthalpy, right? What were the SI units for enthalpy? Kilojoules per kilogram. Right? Kilojoules per kilogram. Look at the definition for H is equal to U plus PV. You can see H has the same exact SI units as U. And PV has the same exact units as U. The product of P and V. All right. Don't you remember that being confusing? Hold it. We have two things with the same units? Yep. And they're not the same thing. Well, guess what this E is right here in the exergy? Well, let's just call it exergy. That's its name. E is exergy. All right? Guess what? Guess what its units are? Kilojoules per kilogram. What? I have three things with the same units. And guess what E sub F is? That's the flow exergy, right? What are the SI units in the flow exergy? This is kilojoules per kilogram. I try to point this out. You ever walk down a hallway, somebody just mopped the floor, where they put a little sign out that says slippery, wet, caution? I'm doing that right now in lecture. Slippery, caution, wet. Be careful here. All four of these terms, they're different. They have different meanings, different uses, and they have the same exact SI units. All right. Here is a summary of what we just did. I built it up, but there it is, typed out a little cleaner. Notice this was never defined. This book, but you could find another book, I'm sure. Oh, I like to define that group of terms and give it a different name. But in this text, it's never really defined as some sort of flow energy. No, no, no. It's just enthalpy plus 1/2 v squared plus gz. Otherwise, if they would have defined it, can you see it would be a nice parallelism, the whole thing? But anyway, there you go. There's no way to do this derivation in 6 minutes unless I really go fast. I recorded it before. Do you want to break early, or do you want me to go fast in 6 minutes and do the derivation? Go fast. All right. So to derive this equation for a closed system, Exergy, what you do is you start with the system at a given pressure and temperature, shown in blue, and the environment, shown in purple, with the dead state temperature T0 and pressure P0. The combined system can produce work. Remember, you could start with a high pressure, high temperature system. Think about an environment that's low pressure, low temperature, or you could just flip it around. You could get work out of a cold vacuum system to start with. So here we're showing that the system is actually in red going to expand and push into the environment. But that's a not useful work. The only useful work is what comes out of the combined system, and so they put a subscript C on this W. What is the subscript C for? Combined. What is the two things that may combine for the analysis? The system and the environment. All right, that's hard enough to explain. You do an energy balance on the combined system. On the next page, we're going to do an entropy or second law analysis on the combined system. You're also going to do energy balance, first law, on the environment only, as well as the second law on environment only. So we're going to go first law for this, first law for that, second law for this, second law for that. Combine it with a lot of algebra and you get the result. Let's go through it. So you say the first law for the combined system, and there's no heat transfer from the combined system to the rest of the world, the surroundings. So that's 0. So you say the work that comes out, what we're really interested in, the work out of the combined system is the negative, the change in the energy of the combined system, which is expressed as both of the system and of the environment, 2 parts to it. And then we expand out change in internal kinetic potential energy of the system, and then the change in internal kinetic and potential energy in the environment. And the environment's just sitting there, big old environment. It has no kinetic and potential energy. It's just at that dead state temperature and pressure, so these 2 terms are gone for the environment. But this term right here for the environment, we've got to do a lot of work to get something so we can substitute in and move to the next page. Well, you do a lot of work by going and doing a first law for the environment and the second law for the environment only. And manipulate it, and this is what you get. In the interest of time, I'm going to just say that's what you get. Please check me on it if you like. Now that I can eliminate this term, the change in internal energy of the environment, combine them with these other terms, we go to the next page, and that's what you get. But you get, from the second law, you get entropy. What's that sigma represent? Entropy generation. So we have a second law for the combined system. Entropy can be generated in the system or in the environment. That's the combined, it's like sigma C. There's no heat transfer out of the combined system. So now you can multiply by T0, manipulating the second law. You get an expression right here. And you see that T0 times the environment, hey, that's right there, minus T0 times the change in entropy of the environment, hey, that's right there. I can now replace those 2 terms by that term, and voila, little algebra, And we get that the change in the energy of the combined system, which we said from the first law is the negative of that is the work out of the combined system. We get this nice packaged equation that says the work out of the combined system is this. Whoever did this first was an absolute genius. But if you want the maximum work out, don't subtract anything. Don't subtract anything. So how do you not subtract anything? Let sigma be 0. What does that mean? No irreversibilities, no friction, all those bad things, right? So to get the maximum, let sigma be 0. When that's 0, you just do name calling. You just say, look it, the maximum work out, everything else over here is just properties of the system with environment, known T and P naught. So they just do name calling and say that's our new property called Exergy. Thank you for your attention. We'll see you next time.